Hello, and thank you for coming to our webinar, AI, ML, Hype versus Reality. So I'm here with Jenny Ravi, and we're going to talk about AI, some of the basics of AI and ML, and some of the things that you need to know if you're getting into this industry. Now, remember, your sound is going to come from a computer, not from a phone call. And sometimes if you have some audio problems, it's helpful to just close it down and restart. We will have questions at the end, and this will be recorded and sent out in an email in a few days or so. So how are you today, Jenny?
I'm doing well. How are you, Jeremy?
I'm doing well. I'm really excited for this webinar because I think it's going to be very interesting, very exciting. So
Awesome.
I always enjoy your presentations on this stuff, even though I don't know very much about it still. So,
Thank you.
but it's always interesting and always fun. So yeah, so let's jump into it.
Awesome. So I'll get started. Just let me know if you can see my screen. I never know whether everyone else can see it or not.
I can't see it. It looks like there we
Pink?
go. Yeah, there we go. Yeah, the screen was a little bit off, but now we can see it.
Awesome. Then we can get started.
All right, awesome.
All
And
right.
when you're done, I can gather up some of the questions and we'll go through those and yeah.
Yeah. I think it should take about 50 minutes. So I'll definitely have like 5 minutes or so or more for questions.
All right, perfect.
Cool. So, hi everyone, welcome to this talk AI ML hype versus reality, complex problems, simple solutions. Now, before we go any further, let me talk about the difference between AI and ML. Now, I use these words interchangeably all the time, and I know many people do, but there is actually a subtle difference between artificial intelligence and machine learning. And I think by far the best definition that I've seen is by Bernard Marr of Forbes. So, what is artificial intelligence? Now, artificial intelligence is a much broader concept than just ML. It's the idea that machines can carry out tasks in a way that we would consider smart. A voice enabled speaker, that's smart. A robot is smart. A walking dog, a robot dog, that's smart. Those are all examples of artificial intelligence. So, what is machine learning then? Machine learning is one application of AI, and it's based on the idea that we should be able to give machines, our computers, access to a whole bunch of data and let them learn for themselves. Now, machine learning is an integral part of AI. So, when we talk about AI and ML, we can consider them to be the same from here on in. Okay? Let's set some context before we dive into the technical details. So, here is a headline from a few years ago. Amazon Echo voice commands offer big benefits to users with disabilities. Now, I must say that when I saw this headline, it gave me a warm, fuzzy feeling in my heart, right? That's because I know that voice commands have been game changing for people with challenges, whether there are development challenges or physical challenges. So, AI today has real uses and real benefits. Now, a voice enabled speaker such as Alexa is less expensive than other specialized devices that used to exist before, which means people with challenges can perform tasks that we take for granted using Alexa: reading, watching TV, regulating the temperature, turning lights on and off. And this has changed their lives. So that's amazing. Now, just as I get this warm, fuzzy feeling, I see another headline that looks like this: for lower paid workers, the robot overlords have arrived. Software and algorithms are used to screen, hire, assign, and now terminate workers. I must say that when I read this headline, it gave me pause. Now, the use of artificial intelligence in our day to day life has real implications and poses real risks to our way of life today. Now, AI used to screen resumes, recommend applicants, schedule shifts, those are tasks that we are comfortable with, and they intuitively are, okay. They seem okay, at least to me, they do. But when I see something like AI can now track worker productivity, especially if they are performing mundane, repetitive tasks, they can track things like, how long do cashiers take to scan items? How long does it take to press a shirt? How long does it take to move, like, some kind of box from place A to place B? Now, workers performing these tasks are actually being tracked in real time, and results are being shared with workers in real time as well. And this tracking is used to make termination decisions. And I must say, I'm not sure I'm entirely comfortable with this. And I know others feel the same way. As we are absorbing this, here is yet another headline. Potential IBM Watson health sale puts focus on data challenges. Now, IBM Watson, I don't know if you guys have heard of this particular department within IBM. They have been at the cutting edge of machine learning and artificial intelligence. But when they turned their attention to healthcare, they found that they encountered real problems, and AI was unable to live up to the unreal hype or unreal expectations we had set for it. Right? What they found was it's extremely hard to build and collect data which makes AI useful. Like machine learning does not work unless you have massive amounts of huge quality data. And this data is basically what actions have worked in the past. That's what you need to train ML models. What they found was in the field of healthcare, data was just not available, maybe not in the right format, not in the same place. Imagine all of the clinics and hospitals we have across the US or across the world, that it was hard for them to get all of this data together so that they could build something useful. In addition, they found that there were significant gaps in the knowledge about treating complex diseases, which meant that, a lot of this was not codified, was maybe just in doctors' heads. So, where are we in the big picture today? We know that AI is incredibly powerful and already improving lives, so it's not an abstract concept. We also know that AI is being used in ways that we may not entirely be comfortable with, and AI is harder to get right than some people thought. Now, as you're absorbing the big picture, let's look at one more headline. AI startup boom raises questions of exaggerated tech savvy. Now, this article in the Wall Street Journal is about the general phenomenon of AI and ML not really living up to the hype that they have generated. Now, and in order to back their claims, they have cited one specific example. And the hype here was there was a company, a startup, which claimed to have built software and an AI system called Natasha that allows anyone to build custom software just like they would order pizza. Okay? This was the hype, this was what they claimed. But what was the reality? Documents reviewed by the Wall Street Journal and other people familiar with this, blah, 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 suggest engineer.ai doesn't use AI to assemble code for applications as it claims. Now, what they said was they could build a mobile app just by taking a few requirements and they would automate this process. But what was the reality? What did they actually do? They indicated that the company relies on human engineers in India and elsewhere to do most of that work. Now, this might seem egregious, but this is by no means an isolated incident. And there is empirical evidence that this is not a standalone case. The reason for this is that startups, especially startups just starting off working on cutting edge technology, can raise huge amounts of capital based on ideas, prototypes, or even just the founder's personality. On the other hand, if you think about companies which are post IPO, which have been selling products to clients, they are held to a much higher bar. They have to actually launch a product, right? The product has to be useful. Clients or customers have actually to buy that product before that company is considered successful. Private investors have always loved funding moonshots, and that's a great thing. But at the same time, public markets are much more hard nosed. Now, there is some evidence that there is a lot of hype surrounding AI and ML, but the pendulum now seems to be swinging the other way, and old school software development seems to be back in vogue. Here is another headline from the Wall Street Journal. Our IT is so good, let's sell it, firms say. Now, if you think about it, this is how one of the most successful software stories in recent times, Amazon Web Services, was born. Now, Amazon had all of this infrastructure that they had created for their website, and most of it was not utilized except for very spike periods, right, on sale days. So they thought, why not monetize our infrastructure? So they started monetizing key peak capacity. Well, the rest is history. This is how Amazon Web Services was born, and AWS now is this cash gushing machine. Now, with this context, we know that old school software development is back in vogue. The question now is, was the AI/ML phenomenon all just hype? Well, the jury is still out on that. However, in my opinion, AI and ML can be game changing for any organization. But we as software engineers need to understand the realities of deployed models. We need to understand that model development is completely different from software development. So, what are the realities of deployed models? Well, this is a tale of two life cycles: the life cycle of software, life cycle of models. Now, the hard truth is that software ages like wine. Software that has been around for a while, that has been deployed to production and has been used by customers, is more robust and gets better over time. But at the same time, models age like milk. A machine learning model is at its best just before you deploy to production. As soon as it's deployed, it starts getting old, it starts getting stale. Let's talk about the life cycle of software. Now, software development has been around for several decades now, and it's a mature science. So, we know that software which has been developed and has been around for a while is more robust. And the reason for that is, we've had a chance to go through, look at all of the bugs, all code paths have been tested, usability fixes have been applied. So everything looks good, it's well tested. External changes rarely affect regular software. Even if a change comes through, you have the chance to put out a new feature or put out a patch, which means that you can have steady periodic release cycles for your software. On the other hand, if you've deployed a machine learning model to production, the life cycle of a model is completely different. A model is at its best just before being deployed to production. A rookie assumption would be that your deployed model will work as well as it did in testing. That's because static machine learning models become less useful over time. If you think about what a machine learning model is trying to do, it mimics the real world and tries to give you predictions based on what it thinks the real world is. The real world is constantly changing, constantly evolving. Your ML models need to do the same. If they're just static, well, they become less useful, which means model development is not the same as software development. If you want your models to be functioning well, doing well, making good predictions, you need a constant stream of new data to keep them working. And this new data essentially allows your model to adjust for shifting realities in the real world. As the real world changes, as your assumptions change, your model needs to change. In fact, deploying models is just the beginning. Think of deploying models as giving birth to a child. That's just the beginning of your journey. You still have to feed the child, bring it up, deal with the teenage years. All of that is ahead of you. Just so with model deployment. So, this is what companies see out there today. Models perform well in the lab, but not on the production line. Before you write off ML and AI has hype, let's talk about three simple steps that you can follow in order to get a robust model in production. So, here are the three simple solutions to complex problems. Now, just because these solutions are simple doesn't mean they're easy. They're simple to understand, they're simple to, you know, absorb. So here's the first one: avoid overfitting. An overfitted model is one that does very well in training but poorly in production. Now, overfitting is a commonly studied problem, and there are plenty of techniques available during model development that you can apply to avoid overfitting. The next solution is handle real time data correctly. When you train your model, you're typically using batch data stored in a database somewhere, but your model performs predictions on streaming data. You need to ensure that your batch and streaming data don't follow different paths. And the third solution, babysit your model after deployment. Don't just move on to the next cool problem. Model deployment, as I said earlier, is just the beginning. Now, let's talk about four different problems that might afflict your AI based solution. The first is overfitting, then we have training serving skew, concept drift, and concerted adversaries. Let's start off by talking about overfitting first, and I'll use a very simple visual for you to understand what overfitting means. So, this is the simple solution, the first solution, avoiding overfitting. Let's say your data can be represented on a two-dimensional plane as you see here on screen. Now, in order to represent this data using a model, you can say, I want to find the best curve through these points. That curve will be my model, and we'll use that curve for prediction. So when a new point comes in, we'll use it to predict, with the X value, we'll use it to predict the Y value. Now, a curve has a good fit if the distances of all of the points from the curve are small. So you can see this curve on the screen has a good fit. But what about this curve? The distance from all of the points to this curve is zero. But is this a good model? Well, how do you think it will perform on test data? When new data points come in, will you be able to use this curve for prediction? Well, the answer is clearly no. This model that you see here on screen is an overfitted model. On training data represented by the red dots, it will have amazing performance. But when you try to evaluate it on data that it hasn't seen before, well, it's going to have poor performance. This is why a simple straight line might perform better with test data. It may do worse in training. It may not do as well with training data, but with test data, it's likely to generalize better. So, an overfitted model is one that does very well in training. It has low training error, but it works not so well. It performs poorly with test or real data. Now, the reason why models can be overfitted is that the model has kind of memorized the data that you've used to train the model. This can be because maybe you don't have very much data to start off with. Maybe your model was overly complex for the data that you have. Right? If your model is unable to extract general patterns that exist in the data, then the model will not be able to adapt to new unseen data. And that is an overfitted model. Okay? Now, mitigating overfitting is well studied, and there are many, many techniques available. Regularization is something that you can perform. This is where you add a penalty function that penalizes overly complex models. You can use cross validation, where you have distinct training and validation phases. You can use dropout, that's limited to neural networks. You can use ensemble learning. So let's talk about just two out of four of these techniques. Let's talk about dropout first. Now, dropout is a technique that is specific to deep learning, that is neural network models. This is where the active learning units in any neural network are neurons. Dropout is where you intentionally turn off neurons during the training phase. So let's visualize this. Here is a neural network. Let's say it performs some kind of image classification. This is a very dense neural network, which means it has many parameters and there is a high risk of overfitting. While training this neural network, at different iterations of training, you can randomly switch off, say, 50% of the neurons. Now, by switching off 50% of the neurons, you're forcing the other neurons to learn more from the input data. So, during the training process, you're forced to rely on a much simpler neural network. Whichever neurons are active in this phase will learn more from the data. At different iterations, different sets of neurons are turned off. So each training step will build a different configuration for your neural network, and this will cause neurons to learn more. And finally, when you're ready to use this model for prediction, you'll use the entire network. So dropout is during the training phase only. In actual usage, you'll use the full neural network. Another technique to prevent overfitting is to use ensemble learning. Ensemble learning is not a single ML model. Instead, it's made up of many individual learners. So let's visualize this. So, ensemble learning is a machine learning technique in which several learners are combined to obtain a better performance than any of the learners individually. A learner here refers to a single machine learning model. So here is a visualization. Let's say you have data, and on the same data, you train a bunch of different classification models. One could be logistic regression, one could be support vector machines, one could be naive Bayes. So all of these are diverse predictors. They're all trained on the same data, but they're different models, which means they'll extract different patterns from the input data. In ensemble learning, the final output is essentially a combination of all of these individual models. So, there are important questions you need to ask and get answered in ensemble learning. The first is, what kind of models should these individual learners be? The second is, how should these individual learners be trained? Should they all be trained on the entire data set? And the third is, how do you combine the predictions of all of these individual learners? Let's look at the first question. Now, the individual learners or the models that make up the ensemble can be of any type. There is no restriction on what type of model you should use. But the idea is that each learner should be as different as possible from other learners. This is because if you use the same model in all cases, the learners are going to learn the same thing from your data. If you use different models, you have a decision tree, you have naive Bayes, you have support vector machines, you have logistic regression, well, each model is going to learn something different from the data you use to train that model. The idea is if they extract different information from the underlying data, you can aggregate their predictions and get a better result. So, now in the real world, you'll find that decision trees are often used as the individual learners in an ensemble. Okay. And the reason for that is that decision trees, when they are trained on different subsets of data, can produce very different models. So you'll have, let's say, 10, 15, or even 100 decision trees making up your ensemble. Here is the next question. How should these individual learners be trained? Now, if each model which makes up your ensemble is different, if the learners are different, then you can simply train each learner on the entire data set. But if the learners that make up your ensemble are similar, let's say they are all decision trees, if you train them on the whole data set, each tree will turn out to be the same. No? So, what people do generally, or what the model does, is each individual model is trained on random samples of the training data. So, let's say the first decision tree may be trained on the first 100 records, the second decision tree may be trained on the next 100 records, and so on. So, this means each model is going to learn something different from your data. You can also use a random set of features to train different models. For example, you can say if you have 100 columns in your data, maybe the first learner will be trained on 50 of those columns. The next learner will be trained on a different 50 of those columns. So you can use random set of features as well. Okay? And finally, the third question in ensemble learning is, how should all of these individual learners be combined? So you have the individual predictions from every model in your ensemble. How should their predictions be combined to get one prediction from the ensemble? And this, there are several different ways. So you have all of these diverse predictors. You have one problem instance, and then you feed them into the individual learners that make up your ensemble. And then each of these learners will give you one prediction. And the prediction could be the same or could be different. But how do you take these individual predictions and get one prediction from the ensemble? Now, there are different techniques you can use for this. You can combine the individual learners using hard voting. So, in the case of a classification model, you'll see which class or category gets the majority of the votes, and that majority is then the final prediction of the ensemble. Another technique you can use is soft voting. This is a probability weighted average. So, for every class or category predicted by the individual learner, there is a probability score assigned. You use that as a weight, and then you get some kind of probability weighted average. And finally, you can make things even more complex and interesting by using stacking. Stacking is essentially fitting an ML model on the predicted predictions from your individual learners and then using that additional model to combine these predictions. So that is a third way you could combine the individual learners of the ensemble to get one prediction from the ensemble. Now, that's it. That's all we're going to talk about in the case of overfitting. Let's talk about training, serving, skew. Now, this is our second simple solution where we say we need to learn to handle real time data correctly and ensure that batch and streaming data don't follow different paths. So, let's talk about what exactly training, serving, skew means. Now, if you notice that your models do very well in backtest is when you use a bunch of training data that you have available and you train your model and evaluate your model using that data. But you find that when you deploy your model to production, maybe it doesn't do so well. And an important reason for that could be something known as training serving skew. It exists, it afflicts many models, but it's often neglected. People don't pay attention to it. Okay. Why does training serving skew exist and what does it mean exactly? That's because when you're training your model, you're sourcing your training samples from batch pipelines. Now, all of your training data is likely present within a database in your organization. Maybe not one database, multiple databases, but all of those are batch sources. So when you source this training data and process it from batch sources, you're likely spending a lot of time pre-processing the data, extracting the features correctly, filling in missing values, taking care of outliers. You're processing this data meticulously well for batch data. But when data comes in for prediction, it's probably from a streaming source. You have some kind of REST API with your model deployed behind it, and you're hitting the REST API constantly at different intervals when you get new prediction instances. So prediction data is usually sourced from streaming pipelines. And it might be that you're processing the streaming data in an ad hoc manner with many, many shortcuts. You're not performing the same series of transformations on your streaming data as you are on your batch data. And this is what leads to training serving skew. So you need to ensure that your batch and streaming data are processed in the same manner using the same pipeline of operations. How do you accomplish this? Now, it turns out that this is a well studied problem once again, and there are many architectures that show you how you can combine batch and streaming data. And the most popular and well known amongst these are Lambda and Kappa architectures. Now, both of these serve to combine batch and stream data, but they do it in different ways. And the coupling of batch and streaming data is much less tight as far as Lambda architectures go. And Lambda architectures are just much more robust. They are simpler and more robust. So what does the architecture looks like? So here is an example of one Lambda architecture using technologies from the Google Cloud platform. Of course, there are equivalent technologies for all of this available on other cloud platforms as well as in the open source world. So here we have streaming data from PubSub, which is Google's real-time messaging service, batch data maybe from some cloud storage somewhere. Streaming data goes through a speed layer, batch data goes through a batch layer. But both of these feed into a single serving layer. And your data is then processed for ML models or anything else for visualization from that single serving layer. So, Lambda architectures take a hybrid approach to processing batch and near real time streaming. Observe the basic architecture here. There are three important components or layers: the speed layer for streaming data, batch layer for batch data, and then a final serving layer. In the Lambda architecture, the batch data is often the source of truth. So it's quite possible that you'll take in your streaming data, store it in a batch source, and then process it. Okay. So streaming code is may also be stored in the batch layer because batch is considered to be the source of truth. Okay. Now, here, Lambda architectures, they deal with both batch and streaming data, but there are different code paths, right? You need to maintain different code for the speed layer and the batch layer. You should find integrations where possible, but they're not fundamentally the same. You need to make sure, by inspection during code reviews, that the processing is the same for batch and streaming data. The Kappa architecture, on the other hand, uses the stream as the source of truth. As far as the Kappa architecture concerned, everything is a stream. The general technology that it uses is it retains a log of all of the data that you have, and it then always processes from the stream, and you use a single code path and a single processing framework to actually process your data. Here is a very simplified version of a Kappa architecture. You have batch data, maybe from some kind of cloud or blob storage. You have streaming data from PubSub. Again, we're using GCP technologies, but there are equivalents on other cloud platforms. Both batch and streaming data are processed using the same code. So the code here is data flow on the Google Cloud platform, but there is just one code base. This code could be anything. You could use Apache Flink, which treats batch and streaming data the same way. You could use Apache Spark, which is capable of dealing with batch data as well as streaming data. Maintain just one code base for simplicity and robustness and perform all of your processing operations using that single code base. Thus, you'll ensure that your training and prediction data follow identical code paths, and this will allow you to mitigate training serving skew. Now, we've discussed overfitting, we've discussed training serving skew. Let's discuss the remaining two topics here: concept drift and concerted adversaries. Now, both of these relate to the third solution that we spoke of earlier. Make sure you babysit your model after deployment. Once you're deployed, you're not done. Don't just move on to the next cool problem. Let's talk about drift first and understand what that means. Now, here is a definition. Now, if you think about your machine learning algorithm or machine learning model, what does it try to do? It tries to figure out the relationship that exists between your input data, those are your features or X variables, and your output target or label, those are the Y variables. So, machine learning is all about this reverse engineering to figure out the relationship that exists between your features and your labels. And concept drift basically states that this relationship that you figured out at the time of training your model is something that's going to change over time. So the relationship between X variables and Y variables will change over time. If your machine learning model fails to keep up, well, it's not going to perform well. And this is what I meant when I said machine learning models degrade in quality as soon as they're deployed to production. That's because the relationship that that model tries to mimic might change over time. Okay. That is concept drift. Concept drift occurs because the world changes. The world is changing constantly. Relationships in the world are dynamic and not static. This is true for personal relationships. This is true for relationships that we extract and find or reverse engineer using ML models as well. And concept drift is exactly why rule based systems degrade faster than ML based systems. If you have a bunch of static rules used to classify your data or make predictions, those rules are going to get outdated very, very quickly. And that's because the world changes, the rules are unable to keep up. Concept drift afflicts rule based systems, concept drift afflicts ML based systems as well. Okay. So, concept drift is related to this idea of a regime change or structural breaks in statistics. Something was true for a very long time, but suddenly something happened and it changed. Okay. This means you have to actively deal with concept drift because you have no idea when things change. when things will change. Uh, let's say you're performing natural language processing on text. The way people use words, it constantly evolves. Every generation or every 2 or 3 years, the same word might mean something different, right? This is why concept, this is how concept drift occurs. So, what is the solution? Well, whatever machine learning model you have deployed, constantly monitor to see how those models are performing and ensure that new data is being constantly fed in to retrain those deployed models. The second solution is, once you find that your model is unable to keep up with retraining, don't be afraid of going back to the drawing board and starting from scratch. So, redevelop your models from scratch if you find that retraining isn't sufficient. This is how you deal with concept drift. Okay. Let's look at a visual example of how concept drift might affect your, let's say you're using a classification algorithm to classify movie reviews, right? You want to classify these reviews as either positive or negative. Now, the two features that we're using two features of a review that we're using to perform this classification is the number of words in a review, that's along the y-axis, and the time when the review was posted, that's along the x-axis. Okay. Let's say these are all our data points, and what we found, through analysis and through our ML model, is that if the review has fewer words and was posted very early in the morning, that's when people are kind of grumpy and they're not happy about their movies. So that's where most of the negative reviews are. Positive reviews tend to be posted late at night and have many more words, right? People gush about their movies. Let's say you were using a decision boundary in order to classify reviews. Now, this decision boundary, this is how the machine learning algorithms support vector machines. They work by drawing a decision boundary through your data. So, this is the original decision boundary based on whatever training and test data you had at the time your model was deployed. So, you found this decision boundary, your model works well, you're all happy. But as more reviews are posted, as time passes, new data points come in, new reviews come in with different numbers of words and different classification of positive and negative. So, new points are available as your model is deployed and used for prediction. Now, these new points, notice that there are many misclassifications, you know, your model is basically misclassifying instances at this point in time. So there are things on the negative end which are positive, things on the positive end which are negative. That's because the world has changed and the decision boundary has changed. Your model needs to be updated on the new data to find the new decision boundary for classification. So, this is concept drift, and retraining is how you deal with concept drift. Okay. So, concept drift can occur because you find that the data itself has changed, okay? Or it might occur that because the way you interpret the data has changed. It could be anything, there is no way for you to know upfront. This is why constant retraining and monitoring of models is absolutely required. Okay? This is how you mitigate concept drift. Let's talk about the last problem that we have here, concerted adversaries. Now, no matter what you're doing, which organization you're part of, you deploy ML models, let's say for these use cases like fraud detection, fake news detection, quantitative trading. Whatever organization you work for, that organization is likely to have adversaries. Adversaries who are looking to confuse or mislead your model. If you have a fraud detection model, well, there are, maybe you work for a bank, right? There are always people out there who are trying to kind of thwart your model, trying to get around your model and perform fraud. This will be true no matter what field you're in, what sector you're in. These are concerted adversaries who are trying to basically game your model and mislead them. Now, how do you deal with this? And this is where we come a full cycle. It's becoming increasingly important for human minders for models. Human minders need to validate the decision made by models. If you feel that your models are, getting things wrong, you need human minders who go in and fix these cases where models got it wrong. You go in and see, actually, this is fraud, but our model classified it as okay. Okay. Essentially, with machine learning, we are back to the future. From machine learning, we are going back to manual learning. And this manual learning component is extremely important. And if you think about very large organizations, when they perform these critical operations like fraud detection, this idea of having human beings kind of validate the output of their model is increasingly important. So, thwarting concerted adversaries requires continuous manual learning to complement your machine learning. So, here are the four problems that we discussed: overfitting, training serving skew, concept drift, and concerted adversaries. And we discuss three simple solutions to these complex problems. Okay. Make sure you avoid overfitting. We discussed regularization, we discussed cross validation, dropout, and ensemble learning. Make sure you handle batch and streaming data correctly and ensure that they follow the same code paths, right? And there are different architectures available for you to do exactly that: Lambda architectures and Kappa architectures. And finally, don't just deploy your model and walk away. Make sure you babysit your model after deployment. This is essential if you want to ensure that you are mitigating concept drift and you're dealing with concerted adversaries. Don't move on to the next cool problem. Well, that brings me to the end of this talk. And here are some resources on Pluralsight you might want to watch. It covers a lot of what I spoke about today. Thank you very much.
Thank you, Jenny. That was great. There's a lot of stuff to think about there for sure.
I'm glad you enjoyed it.
There was something that really stood out to me that I'd never
Mhm.
thought about that before is the pipelines, streaming versus batch and the difference between those.
Right.
That's very, very interesting for sure.
Yep. Yes. And if you think about how, whatever models I've trained, I pay so much attention to training, but I'm not, once I deploy the model, I feel that it's just going to work, right? Because I did
Yeah.
so much training on it.
Yeah, like this will be perfect.
Yeah.
That's great. So we do have Q&A available. If
Mhm.
those in the audience have a question, use the Q&A box there on the right.
Okay.
We do have one question here, which I'm sure you've been asked several times. What are some of the downsides of AI advancement that we should be aware of?
Oh, I think it's just basically not realizing how powerful AI is and kind of ending up misusing it, right? AI feeds on data. It's like this hungry monster which is just gobbling up data. And if you, let me just, yeah. And if you, so first of all, there is a massive amount of data available. Organizations are constantly collecting data, but are they collecting data with consent? Right?
Yeah.
So once you start getting into that, you start worrying about how your data is being used. Why am I being shown this advertisement? Those are all small annoyances, but they can get, this can, go on to discriminatory, right? Like if you run a marketing campaign for all of your customers, you have an e-commerce site, how do you know the predictors you use are not discriminatory in some way? Right, and it's inadvertent sometimes because you're
Yeah.
not paying attention, right? You're like, oh, I have this powerful tool. So that's one thing that's worrying. The other thing is, of course, and people talk about this a lot: bias in data. When you collect data, you don't realize that it's biased because you've just maybe tested on one part of the world. If you do all of your testing in Europe, you're unlikely to accurately represent Africa, Asia, and other countries, right?
Yeah.
And that's just one example. And often organizations are placed in a geographical location and they do all their testing in that one place, right? So that's bias. That's one downside. And I can go on about this. There's one more example, then I stop. So the other thing I worry about is AI is so cool and it can do so many cool things that organizations often tend to be very, very aggressive about their use of AI. Like, for example, like I think Tesla is an amazing company and I'm always excited about what they're up to. But if you think about how they've been pushing AI in their cars, sometimes I wonder, like, has it been tested enough, right? Is it really that powerful? Will it always work? You worry about those things.
Yeah, definitely. And there are a lot of, a lot of people talk about the downsides, but there are a lot of upsides when it comes to safety and things like
Yes,
that.
yes.
And
And that's why you can't just say, I'm not going to use AI, right? That's very,
yeah,
it's like, do I be very aggressive or do I be very conservative? And then I lose out on all of this. And this is why, like, I start the talk off when I talk about like how AI has been amazing for so many people.
yeah,
And you can't just wish that away. You can't just say, look at the, and all the headlines are about the downsides, right? Because people don't notice when things are working.
yeah.
So,
Definitely.
yeah,
And there's been ways that I've seen it applied, like for me personally, writing software. For a long time, I had a bias where I'm like, AI cannot replace software developers. That's impossible. It can't write good code. But I started using things like GitHub Copilot and Tab9 and things like
right.
that. And then I realized like it's not trying to replace me, it's trying to help me. Like all these ways I'm repeating
Yeah,
things and so now I'm telling developers, don't be afraid of AI when it comes to these things. It's actually here to help, and it's catching things, before we can as humans. And so I've really
exactly.
enjoyed programming and writing software with AI just because it spots things that are repeating or it guesses what I'm going to
Yeah.
write next. And it's kind
And
of
it's,
nice.
it takes away the, I mean, software programming, there is like 80% mundane, repetitive tasks and 20% creative, innovative tasks.
Yeah.
If you can make that 50-50, our jobs would be amazing.
Yeah, exactly. Let's see. So we do have some questions here. Um, let's see. Uh, did you talk about the weighting for different streams of data and how that is managed, like human determined or ML determined? Is Robert's question.
I'm not sure I fully understood. Maybe you could repeat that.
Um,
Waiting for different.
yeah, did you talk about the weighting um, for different streams of data? And you did talk about that a little bit when talking about the pipeline streams, I believe is what he said.
Right, right.
Was it
And
human
I think
determined or ML determined?
so. I think there is the whole thing about ML is that there are many moving parts, right? So there is the streaming data, there is the batch data, and then I spoke about the predictions and then actually validating those predictions. Now, when you automate something, what you want is you just deploy it and then you forget. It's automated, you don't have to do it anymore. But unfortunately, that's not how ML models work. So there is that human element of it which still needs to be there. And that's why especially in social media, they have these armies of people actually looking through the posts and flagging them. That's needed. That's absolutely needed. You can't just rely on AI algorithms. As far as the waiting for data goes, I think maybe if you're referring to the whole thing is the velocity of data for batch data and streaming data, those are very, very different. And that's why the processing for batch and streaming data generally tends to be different. But if you see, as technologies have evolved, they're trying to treat them the same way. And that's not only for training, serving, skew, and ML. That's because they've realized that you can't differentiate between data based on velocity. For example, if you consider, like, I work a lot on the GCP. If you look at BigQuery, which is GCP's data warehouse, it basically ingests streaming data and allows you to run real-time queries on those streams. And I'm sure equivalent technologies exist on other cloud platforms, except that maybe I haven't studied them. So,
Yeah, awesome. Okay, and James has a question. Um, I've heard people say you need 100% perfect training data to train a model well. You mentioned that you need to treat batch data and streaming data the same, and don't these statements contradict each other?
so I think if you think that your training data will be 100% perfect, you'll never be able to get to a good model, because data is like, just even just think of, like, you go to Kaggle, you're learning ML and you try to work with that data. You have to spend at least like days cleaning up that data. You have all of these missing values. Maybe you just drop them because it's a prototype or something, but you have to deal with dirty data. There is no clean data, there is no 100% data. And even with this combination of batch and streaming data, you're not going to get to 100% parity. There will be cases where you miss out on something and you can't really process it perfectly, because batch data, the whole idea of batch data is you have a global view of the world. You know exactly what the data looks like over time. But with streaming data, especially as things keep changing, you have no global view. So you're doing the best you can with the little window that you have. So it's never
Yeah.
going to be perfect. And this is actually a reason why ML adoption, there is some, um, it's difficult, like especially if you think about regulated institutions like finance or healthcare. It's very hard for them to adopt ML because ML is all experimental, right? You have to keep working with the model, and it's all probabilistic. ML is basically assigning probabilities to outputs, and it's like, this is what it's most likely. I think it's a cat, or I think it's a dog. Now if you're differentiating cats and dogs, this probability is totally fine. But if you're looking at a tumor and saying whether it's benign or malignant, that probability is kind of scary. So
Yeah, that's interesting.
yeah.
And here's another one here that says, so it sounds like human is still the ultimate source of truth and correctness. Does adversarial training methods change this?
So I don't know if I agree with the first statement, because clearly we are very, very biased. If I say something is right, I'm sure Jeremy will say it's wrong. So on something, right? It need not be on everything. We might agree on most things, but we'll have things where we differ. In the end, though, if you like, let's say for fairly neutral things, if you remove all your bias and everything is, masked out, we are still able to make better judgments than models. We just can't do so at scale, right? It will involve like thousands of us just sitting around and classifying things. That's not going to happen. It's very boring. And Sorry, what was the second part of it which I wanted?
Does the adversarial training model
Yes.
change that?
So those are amazing though, but that's not, so the way these adversarial models work is, what you're trying to do is generate something new, just like humans do, right? So adversarial training models can generate images, which is like art, based on real art samples that you feed in. So that's the generative portion. And then the adversarial or the discriminator, basic, so you have something which generates images which are clearly fake, synthetically generated. You mix that in with real images, and the discriminator tries to figure out which is real, which is fake. So the generator and the discriminator kind of competing with one another and trying to figure out who wins. Now obviously both get better over time, so at the end the generator should be able to generate content which looks like the real one, right? But this doesn't work till you have real content to start off with. So you need the humans to generate real content before you can get the models.
Yeah, that makes perfect sense. So here's another question. I have a large set of pre and post manually cleaned product data. Would this be a good use case for machine learning? If so, where would you recommend to start on this project?
Uh, I think it depends on what data you have. If you have product data and customer interactions with product data, that would be a recommendation system. Uh, and if you have product data and you're trying to maybe, you don't have any labels maybe, and you're trying to categorize products, you'd have to like convert all of your product data into numeric features, and then maybe you can do some kind of clustering to find out which products are like one another. So it all depends on what data you have and how well you're able to express your data in numeric form. If you just have like product text, for example, people have done cool things with text. They extract like these dense vector embeddings of text, and then try to see which products are similar to one another based on these embeddings, right? So there's a lot of cool things you could do. In order to know how to get started, is first you have to look at your data, then maybe just have, I don't know how far advanced you are in machine learning, but have an idea of the basic use cases of ML for different kinds of data and for different kinds of prediction, right? Is this a classification task? Is this a regression task? Is this a clustering task? And once you know like the broad categories of problems, then you can look at your data and then you'll get ideas.
Awesome. That's great. Well, thank you very much for this presentation. I think this has been really, really great, and
I'm happy
really
to be here.
appreciate this. Any
Thank you,
final
Jeremy.
words for anybody watching today?
Basically, I think embrace AI ML. They are super exciting and they are getting democratized. It's you don't have to know to code to apply ML. So I think explore those if you feel that I don't know how to code, I don't know how to get into this field. That's no longer a barrier if you're working on a cloud platform. So don't be discouraged. And obviously you can learn to code along the way if you're interested, but that's no longer a barrier. And at the same time, when you're using ML within your organization, think of its implications, right? We don't want to be headlines in any newspapers. We want to be footnotes.
Yeah, that's always a good rule. All right. Well, thank you very much again, and we'll wrap this up. And we will be sending out a recording of this in a few days with the slides, and we'll send out some links to the courses that you mentioned for folks getting started.
Sounds good. Awesome. Thank
Good.
you guys for having me.
Yes, thank you for doing it.
Bye bye.